So, as the title hints at, I'm going to talk to you today about algorithms, and I'm going to try and give you a more quantitative view of algorithms than I suspect you've been able to see, particularly if we think across algorithms. And I want to think about that in the context of AI and big data, because I think when we think about big data, we usually think about this, right? Moore's law. Right? So this is Ray Kurzweil's version of this. Has a nice advantage going back to 1990. But you have this, on a very exponential logarithmic scale with very big jumps, right? You see this very, very long historical improvement in information processing. And we say, this is incredibly important, and it absolutely is. But it is only part of the story. And I would argue that it's the part of the story that's actually easier to see. And what I want to tell today is the other part of that story, the algorithmic part. Okay. So what do I mean by algorithmic progress? Well, I want to think about algorithms in a very specific way, right? I think when we talk about them in the general world, we think about this as sort of like, oh, you might have like a different software program or something like that. We'll talk about algorithms in a very loose way. I want to talk about this in a much more computational science way. And I want to motivate that by a very sort of agnostic way of thinking about it. So I want to have something that I care about, which is like, I want to get some number of tasks done in some unit of time. Okay, very general, seems very reasonable. And all I'm going to do is create a mathematical identity here. So I'm going to divide both the top and the bottom of this by computation, right, and expand it out. I'm going to get the number of tasks I can do for a given unit of computation, the number of computations I can do per unit time. And what I like about that mathematical identity, right, is this actually clarifies here, right? This is what we're talking about when we talk about Moore's law, is our hardware speed. But we have this other piece here about the number of tasks I can do with a given amount of computation. And that's a productivity measure, right? We just had Raj talking, right? This is, economists are super, super stoked about productivity improvements, right? Because it says with the same amount of inputs, you can just do more, okay? And so what I want to do today is to talk about and think about this contribution as playing a role in this. Now, this idea that this is important goes back to the very beginnings of computing. So Ada Lovelace, in her notes on Babbage's analytical engine, I mean, really, the beginning, says in almost every computation, a great variety of arrangements for the succession of possible processes is possible. One essential object is to choose that arrangement which will tend to reduce to a minimum the time necessary for completing the calculation. Right? She's highlighting that there are these more efficient algorithms that are out there. And so a very simple one, my apologies for those of you who are deep in algorithms, but just to get a sense of this, so sorting, something we often want to do. So imagine we're sorting this set of balls from, we want to get them from smallest to biggest. So bubble sort as an algorithm says, what I'm going to do is I'm going to compare these first two, and if the bigger one is on the left, I'm going to move it to the right. If I swap them, now I get this one. I move my frame over, I consider these two. Okay, they're already in the right order, so I don't want to do anything. I don't change anything. I move over to the next one. These do need to get changed, so I change them. And now I've been on one pass on this, right? And I've successfully moved the biggest ball to the right, right? I would then start at the beginning again, and I would do this, and I would have to iterate through this enough times to get these in the right order, okay? Turns out if you actually look at the computational complexity of that, it's n squared minus n, or as is often written by theorists, order of n squared. Okay, if we think about that as compared to, for example, quicksort, same list of things. What we do is we have a cutoff. We say, are you above or below this? We put everything that's below it on one side, everything that's above it on the other side. Then we do that iteratively on these ones. We very quickly get to our answer, right? This has an algorithm of order of n log n, which actually is the optimal that you can do. Okay, so what I mean by algorithmic progress, right, and it's more concrete, is just this sense of like, if you were using this algorithm, right, and you move to that algorithm, you get a lot more done through your computation. Okay, now, does this actually turn out to be important? Well, according to the President's Council of Advisors on Science and Technology, yes, very, very important. In fact, what they said, in many areas, performance gains due to improvements in algorithms have vastly exceeded even the dramatic performance gains due to increased processor speed. So I read this, I was very excited about this. I said, fantastic, I want to go back to the citations and I want to see the data on this. And unfortunately, you get back to one example, right? And this is solving linear systems. And you're like, okay, And you go back and you look at other people who've done this, and overwhelmingly, there are like 6 or 7 people who've done this analysis on linear systems. And indeed, you do get this result. Part of my training is economics. I'm not very happy with that as a sample. I want to go more broad. But now you're going to run into a problem, right? And that problem is which algorithm problems to include, right? Like there are an infinite number of algorithmic problems you could write down. What are the ones that I should actually be measuring to understand it? So our solution is, as a first pass, is to say we're going to prioritize the problems that we teach to computer science students based on the data we're going to gather from textbooks. So we're going to go to textbooks and we're going to say any algorithm that is in one of the textbooks we look at, we're going to include. So we're very inclusive in this definition. That's going to then give us this sense of, okay, what are algorithms that we think are at least important enough that we want to teach our students, and we're actually doing. Okay, for what's going to follow, I'm going to focus specifically on worst case asymptotic time complexity. For those of you who are not in this particular area, most of that you don't need to worry about. The key part here is the asymptotic time complexity means that if we have lower order terms with the constants, we're going to be ignoring those. We actually did a bunch of testing. It turns out not to matter. It's fine to do that for the kind of stuff we're doing. Worst case here is just like it's not an average case. Like sometimes, if you look at a different distribution on these things, you'll get a particular one. We're looking at the worst case one, which is actually generally what theorists look at.
Unlike the quicksort example from the last slide, actually, which is worst case and squared, but average case.
No, that's those are worst.
Sorry.
Yeah. So yeah, both of those are worst case.
If the pivot is always not.
Oh, right. If you have no knowledge of the distribution, then you can end up with it. That's true.
Yeah.
Yes. Okay. For the results I'm going to show you today, I'm going to look at specifically exact algorithms, right? What we have done since these results, we actually have it now for some approximate algorithms as well. So I'm happy to talk about that if that work is not yet published. And then lastly, we're going to focus on ones that are parameterized by the input size, n, right? And that's obviously going to be very relevant today because I mentioned I want to motivate this by big data, right? And part of this is going to come out that, of course, algorithmic gains are going to be larger. And if you go from n squared to n log n, that gap of log n is more valuable to you if you have a bigger n. And that's going to push you towards big data being helped. Okay. So what did we actually do? Well, full credit to my student who spent a huge amount of time on this. So what we're going to do is we're going to pick the main areas of computer science. These are the first set. We've got another slide as well. We're going to go and find one algorithmic textbook or one textbook from each decade, as much as we can, like the most cited one or the most downloaded one or whatever. And we're going to, as I say, go through all of them to find what are all of the algorithms that are mentioned in those. Okay, so my student went through 57 textbooks. That's great. That gets us these ones. But then we're going to do something even more time-consuming on this, right? Because we're going to say, okay, well, we saw that sorting was in there. But we're not interested in just like a particular sorting algorithm. We want to know the history. So we're going to go back to the literature and we're going to go to all of the previous sorting algorithms and all the subsequent sorting algorithms in order to get the full history of these things. So we went through 1,100 research papers in order to do this. Okay, so this was a very time-consuming project, but we thought very valuable because now you can see we have a much more complete version of this question than we asked before about how important algorithms could be, and not just one version, but a more broad one. Okay. So let's see what this looks like for a couple of these. So we're going to organize these in what we call algorithm families. You can think of these as being successive versions of a particular algorithm. So let's start with maximum separate. So if you don't know, maximum separate is this idea. Take a whole big long set of numbers, some positive, some negative, and you want to make a decision where you start somewhere and you finish somewhere, and you want the sum of what's in between those things to be the maximum, right? So if you are, like on the stock market, this is like buy low, sell high, right? But it's used for lots of different things. So if we start in 1969, where the problem is first introduced, there's just a brute force way of doing this. And that brute force way is an n-cubed algorithm. Okay? Not very long after it's introduced, we see Bernander comes up with a better algorithm for this. And in fact, that algorithm is so great that if your problem size is 1 million, right, that jump means that in the same amount of time it took you to solve one problem before, you can now solve 1 million problems. Okay, nice job. Almost immediately thereafter, Shamos comes up with a better algorithm, and then not long after it came with an even better one. And so what we can see is for maximum subarray, over this time period, we have a trillion-fold improvement in algorithmic performance. Right? In the same amount of time, you can do 1 trillion times more. Now, for context, right, this is charting Moore's law from 1983 to the same time period, right? And you can see we are, way, 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 way less.
But that problem size in a million.
Well, okay, so great. So this is a great one. Okay, so as I mentioned before, one of the things about these n's, right, is the bigger the n, more important it is. So absolutely, right? So you can do this calculation, and in fact, we've done it. Say, well, okay, what size would you need to get equality on these things? For example, where the contribution from Moore's law is equal to the contribution from algorithms and so on. Exactly. So what we've done in the paper is what we do is we just do it for several different reference points. So we say problem size of 1,000, problem size of 1 million, problem size of 1 billion. Like, let's think about a range that people might do either for stuff in like a typical business versus stuff that you might do in like a large data problem, and try and get some sense of the scale of it. And actually, in a couple of slides, I'll give you some specific numbers on it. Okay. So there are a couple of things I want you to notice about this, right? So we pulled out 3 examples here, right? The first is maximum subarray, huge gain. Self-balancing tree creation, no gain at all, right? And then polynomial factorization, we get some gains. So the first thing is, like, there's lots of heterogeneity. Like, one of the weird things about Moore's law that is very unusual in innovation is it was a very steady process that improved almost everything at the same time, right? We see that not at all with the algorithmic improvement that we see. Second is we get, these like big jumps that are happening very, very quickly, and then you often have decades, right? So it's like, it's a very sporadic thing. Nevertheless, what you can do is think about, well, if we think of from when it was first discovered to today, what's like the equivalent level of improvement, like the equivalent compound year-over-year growth, right? Now, we have to be aware if we're going to make this choice, right? Like, we know it's going to happen in these big steps. But it's so useful for saying, over the life of these algorithms, how important have they been as compared with things like Moore's law? So now maybe I'll pick a number that a little happier for you. So I'm going to pay only 1,000 this time. Smaller one. And what you can see here, so now here on the x-axis, we have the percentage improvement year over year. So that's that compound growth rate that would be equivalent to the total gain. And we can see that 64% of the algorithm families, or you can equivalently think about this as algorithm problems, improve between 1 to 10% per year. Okay, that's like, if you're an economist, this is a big deal, right? The economy as a whole improves about 1 to 2% per year, right? So any parts of the economy that are improving faster than that, we like a lot. But, it's not that fast. 13%, 10 to 20%. So we have this, part down here. Now, it is worth saying, we also have the stuff up here, right? 100 to 1,000% improvement per year, over 1,000% improvement per year. So what's happening here? These are things that are falling from exponential time into polynomial time, right? So it used to be basically almost impossible to solve these problems, even on a scale of 1,000, right? And now with this, they become possible. Okay. Now, I mentioned, the importance of this n that we chose, which absolutely, these are just arbitrary numbers. Let's actually look at what that looks like if we take 1 billion as our number here. And notice how much this distribution has shifted over, right? So we still have some at the left-hand side here, 45% that are moving pretty slowly, but we can see now these gains are quite large. And in fact, we can divide it up, as I've done here with the color regions, to say these are faster than Moore's law, these are slower. And we can see that 43% of these problems, the algorithmic progress for this size of problem was more important than what was going on with Moore's law. Okay. Yeah.
One aspect of Moore's law is said that hardware builders sort of use that as a guide. Like, what does Moore's law say about what we should do in the next year or two? So it's a different kind of log, and this seems much more natural.
Oh, yeah, okay, it's great question. So there's this, like, what I've been talking about just so far is like the contribution of these things, right? But one of the things you can ask is this idea of like, well, why do we get it and what does it tell us about the future, right? And you're exactly right. So my group has done some work where we've studied the roadmap for semiconductors, right? And what you can see is precisely the problem is you have to coordinate a huge number of different technologies and different number of scientists in order to get Moore's law to continue, right? Because you have to say, well, we're going to need better focus on our lithography. We're going to need different types of materials. We're going to need more pure silicon, et cetera, et cetera, et cetera. And so precisely they lay it out. And if you were like, oh, I'm going to go twice as fast, what you'd find pretty quickly is that one of the dimensions you needed to keep improving wouldn't work. And so over the lifetime of Moore's law, you do see like slight accelerations and decelerations, but it's always on the margin. It's never really throwing the whole thing out, I think for exactly the reason. It was a very useful coordination device for the industry to do. Yeah.
I don't know if you've looked at that or not, this is super interesting, but what about problems that don't have a specific solution? I mean, most of the stuff that a lot of us are doing in the computer now, you open Photoshop. Most of the algorithms it has there, they don't have a single right answer. You could iterate and find better algorithms. A lot of you mentioned theoretical computer science textbooks. A lot of the undergrad curriculum on algorithms and theoretical computer science is approximation algorithms. It's not precise maximization.
Absolutely. So that is in fact what we have. So I want to divide up my answer to yours into two parts, right? So there's one which is like heuristics, and there's one which is approximate algorithms.
Yeah, but it's more than heuristics. I mean, in neural networks, which is something a lot of people in the audience are thinking about, transformers, whatever. These are all attempts at approximate solutions to problems that we cannot solve completely.
Absolutely.
So it's
right. And so the AI question I'm going to hold off because I'm going to show you a whole bunch of stuff on algorithmic improvement in AI specifically. So we will get to that one. But more generally, to answer your question, if we think about heuristics and approximate algorithms, so heuristics we don't include here. So heuristics is like, hey, it's often useful to do X, right? That ends up being super, super dependent on what the data specifically looks like, right? And sometimes they're correct and sometimes they're not correct. So that's very hard to analyze in this kind of a framework. But approximate algorithms we have looked at. So that's a paper we will hopefully be submitting in the next couple of months. But we have exactly done that kind of analysis where we say people can give you a guarantee and say, I can get you within 1% of your answer. How much of benefit does it give you? And we actually see some substantial gains in some places.
so and the general message would be the same as the one that you're telling us about today from that analysis?
Yeah, so I mean, so what you see in that is that like many fewer problems admit approximate answers than you might expect, at least. So that's what the literature has seen so far. So it's not that we get sort of like a whole big thing on everything, but definitely some problems get quite substantial gains.
Thank you.
Okay. And by the way, for those of you who are using algorithms and are interested, so all of this data gathering, we've made this into a public repository, Algorithm Wiki. Look it up, and you can actually see time complexity, space complexity, and a whole bunch of other things, which could be useful for the problems. Because one of the things we were quite surprised by is like actually you often didn't see the optimal algorithm being listed in a textbook or something like that. Okay. Artificial intelligence. So I want to start, and I think you're going to have maybe a talk tomorrow as well about scaling laws, but I want to talk about the power of scaling up these deep neural networks precisely because it is such a dominant way of improving, but it also implies a whole bunch of resource constraints that are going to be very important. So here's my just favorite example of this. People may have seen, so this is a 2022 Google paper. So it's a mixed multimodal model where you give it the prompt, a portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses, standing on the grass in front of the Sydney Opera House, holding a sign on the chest that says, "Welcome, friends." Great. And obviously chosen because like this is not, you can't just pull an example from the web, right? This does not exist at the point where they do it. Fantastic. If you do it on a deep neural network with 350 million parameters, you get a chihuahua, Right? It's not really a kangaroo, like, that's not the Sydney Opera House, that sign is wrong, like, we're not that close. Okay, same training. Now 750 million parameters. Okay, that's starting to look like the Sydney Opera House, right? We're not there. That sign is totally wrong, and this is starting to look like a kangaroo, but it's not the one in the orange hoodie. So still not that good. Okay, 3 billion parameters. Okay, now that looks a lot like a kangaroo and the right thing. And this sign, if you sort of squint, looks like it says welcome friends. It doesn't, but it's kind of close, right? And then there's the second sign, that's just wrong. And you know, the Sydney Opera House is not like a million of those things, but we're getting closer. And finally, 20 billion. Pretty amazing, right? Okay. So sign is right, glasses are great, like kangaroo is great. Okay, so huge benefit from scaling. But this is all the same model, right? What we did here is we scaled up. This also comes, as I mentioned, with resource constraints. So just to give you some sense of this in a very sort of concrete way. 2012 with AlexNet, trained for 6 days on 2 GPUs. And I remember when this it was a bit scandalous, like how much compute had been used for this, right? 2016, Google Neural Translation Machine, 6 days on 96 GPUs. And GPT-4, 100 days on estimated 25,000 GPUs. And we now, we have multiple people now building 100,000 GPU clusters in order to process these things. Okay, so what underlies all of this, and some of you may have seen this, is these scaling laws. So if you haven't seen this before, here we have compute, and this is a slightly faded one, but each of these is a factor of 100 increase in the amount of compute you use to train your model. And this is the error that you're going to get as measured by, I think this is cross-entropy loss, if I remember right. And what we have here are traces of as you train the model, right? So if you pick a model with a certain number of parameters, you can sort of follow it down and you see it improves quite rapidly. And then at some point it approaches the asymptote here and then it goes off. And if you use a smaller model, you get there earlier, right? If you use a bigger model, you get there later. Okay, so this is quite powerful, right? I think this is, one of the most important things going on in AI right now is just driven by these scaling laws. Importantly, this also gives you a recipe, right? It says if there's a particular amount of error that you want, right? You can actually say, well, I should train this kind of model up to this point, and gives you a recipe for actually how much to do. Now, okay, so I already said this. So these exist all over the place with deep learning. And these can emerge both from the way the sampling is done with data and also with the way the parameterization is done. I'm happy to talk about that more afterwards if people are interested. But you end up with these scaling laws all over the place, right? Images, turning image to text, videos, math, all of these things. Okay. Now, what is not usually shown, but I think is really important when you think about this, is these are all power laws, meaning that there's a very specific behavior that happens. So if you want to say, well, I want to have the amount of loss that's left, so I want to move from 50 to 25 or 25 to 12.5 or so on, right? I have to increase compute by a certain amount. For images, that's 40x. These are pretty small images, that's why this goes up if these are bigger. 100x for text images, videos, 140x, etc. Language, 1.9 million times. Okay, I want that to sink in, right? Because people are building systems on the order of $1 billion, right? And so, if you had to scale up like this and there was nothing else going on in terms of improvements, right? This would mean you'd be at the scale of the world economy in order to have all of these, right? So this is why we're just getting so big so quickly. Okay, and boy, are we, by the way, to give you some sense of this. So OpenAI says this very explicitly. We believe that scale in our models, our systems, ourselves, and our processes and ambitions is magic. When in doubt, scale it up. And people have. So this is the amount of training compute actually used in these different models. You can see we have language, vision, and multimodal models. Since 2017, we've been increasing the amount of compute by 10x every year. Just a giant increase in this, right? And as I say, like absent anything else, a 10x increase in your model and your compute costs you 10 times more to run those, right? You have to run your GPUs for that much longer. Okay, so we're definitely not at the end of this trend. So recently, the Anthropic CEO said that leading AI models will soon cost 10 billion, and slightly absurdly, Sam Altman was talking about getting $7 trillion in order to build new semiconductor fabs and stuff like that. Okay, but we're talking very, very big. Okay, now this sounds like a story, therefore, that is all about the amount of compute that you throw at it, right? But of course, given the title of my talk, I want to talk about algorithms here. And I want to compare them to hardware improvement, right? Because that's been our reference from before. I want it to be again. So this is no longer Moore's law. This is GPU performance. So each of these is a GPU from NVIDIA over time. You're looking just at the data center ones. And we've normalized everything to 2009. Okay? And so what you can see here in the purple is that the improvement in floating point operations, either 16, 64, or 32-bit, whichever one you want, is improved by between 60 and 70% per year, compounded, right? That is very, very fast. Price has also gone up 25%, right? But you can subtract these away and you still end up with very, very rapid improvement, right? In fact, faster than Moore's law, which is kind of interesting. All right, so that's going to be our reference, right? So we have something like a 45% improvement year over year in the cost performance of GPUs. That'll be our reference as we think about from algorithms. All right, so this is a paper that we did with some of the folks at Epoch AI. And what we're going to do here is we're going to say, when GPT-2 comes out, we're going to call that amount of compute 100%. And that's in 2019. And then we're going to look at when other models can achieve that same level of performance, right? So for some later model, you might only be halfway through the training run, right? And that's, you get to the same level of performance, and we record that, how much compute that was, right? And that's going to be our reference. And what you can see is from 2019 to 2021, we dropped down to well less than 1% of the amount of compute needed to get to that same level of performance. In fact, the doubling time on algorithmic efficiency is less than 6 months. Right? That's, at least for me, that's pretty shocking, right? Every 6 months a doubling, okay? You can pick another one, you can pick Gopher. This is 2021, carry it forward again, in just like a year and a half, you're at like 20% of the amount of compute. In fact, across all of the language models we analyzed, we find that the average doubling time is between 8 and 9 months. So that is dramatically faster than the 45% improvement we just talked about for hardware, right? Algorithmic progress is much more important for what's been going on in large language models than is the hardware improvement that we've seen from GPUs. Now, both are important, but yeah.
I'm curious, have you looked at anything similar for the cost of inference alongside training? Because I think that's also substantially cheaper over time.
Yes, so we haven't looked at it specifically. So there's a paper. So there's a series of papers that we've done, and OpenAI did some, where we looked at like how models are changing and stuff like that. So you can sort of infer the one, but I don't actually have a specific number for it. Okay. As you can imagine, I mean, like whether you get all of this in inference basically depends on how much any particular improvement is either resulting from you need less data in order to train the model, right? So we know the data efficiency is getting better, learning rates, fewer epochs, stuff like that, right? But then the other part is like, can you build a model that uses fewer parameters to do it? And so in so much as it's the fewer parameters, then it would translate directly into inference costs. Okay, so having just said that then, let's now go back to the context of all this improvement we just saw coming from making these models bigger, and let's say, all right, they're getting bigger, but how much play did the algorithmic improvement have on them? Okay. So first I want us to focus on the blue, right? This is going to be physical compute scaling. Again, we're gonna normalize here to 2014, and we're going to say, okay, you compare to models from 2014, how much of a scale up did you have in actually the number of flops you really ran, right? And the answer is 17 million X. Okay, that's a really big number. If you hadn't had algorithmic progress, you would have had to pay an extra 22,000X on top of that as a factor. Okay, so what I find interesting about this graph is, I mean, it is telling you that, like, just how important this algorithmic progress is, right? But it's also telling you that for these really, really big models, because we're scaling up by 10X per year, right, that we are nevertheless, that is still a bigger factor in the cutting edge, right, but not for a particular level of performance. And so
how does this, sorry if I may, there is a third thing that seems to be relevant here, which is the quality of data and the amount of data that they have to train on. That has also improved drastically over these years.
sure.
How do you account for that?
Right, so that would be included in this algorithmic progress, right? If you figure out, like, actually, if I, like, you know, of these 10 pieces of data, actually all of the information is in these three, I only need to train on these three, that would count as algorithmic progress in this, absolutely.
Thank you.
Okay, so I just, like, I think it is important enough to, like, I think we should be thinking about when we talk about improvement in this. I think part of the reason that algorithms do not get the sort of credit they deserve on this, right, is that we don't have a good name for them. So I want to propose one. So people may know in climate change science, right, people talk about negawatts. So negawatt is a unit of energy saved as a result of conservation measures, such as reducing the use of heat or electricity, right? And if you look at when people talk about, oh, how are we going to meet the energy needs of 2050, they'll say, well, we're going to get this from this, and this much from negawatts, because we're going to have conservation measures that mean we don't need that anymore. And I think we should have a new term, megaflops, right? Megaflops are, we don't even need to do this operation because I thought cleverly about it and came up with a better way to have the output. Okay, so off my soapbox, but I think it's, you know, I think it's very important to be thinking about this and how important it is, because as you said, 22,000X, it's a big deal.
And also the literature does not at all consistently quote the amount of computer training resources.
Oh, yeah. Yes, it is. A constant refrain that we have in my lab, right, is this great frustration of, like, we do these comparisons and you probably read 5 to 10 papers to get one that has enough information to actually report these things. Absolutely. Yeah. Okay, so I just want to end with this just for a framework about thinking of the future costs, environmental and stuff, right? What I showed you is that scale up in models is big enough that the cost of cutting edge systems is going up like this, even despite hardware improvement and algorithmic improvement. But the cost for a given level of performance is falling dramatically because of the improvement in algorithms and hardware, right? And so this matters, for example, a lot to the discussion that we're having right now about the energy needs, right? So, for example, the state of Virginia has just made their predictions for how much new energy they're going to need. And basically all of the increase that they're going to have, they imagine coming from data centers, right? And the question is, like, okay, well, if we have all this improvement, right, that's going to take down the cost of a particular level, but we're also going to be building bigger models, and we're also going to have more adoption. And so it's that complex interplay that actually is going to matter here. And so we and others are working on that question of how to make those predictions. But it's really important when we think about these things, not to just think about it statically as, like, how much are these models using today? We need to project forward these trends. Okay, so in terms of the AI side of things, and I'll get to my last piece here, but in terms of the AI, I think it's important to say that two big phenomena are happening at once. These cutting edge models are getting more expensive over time, but the cost of models with a given level of performance is getting less expensive. Deep learning success relies on flexibly modeling data, and these models are getting ever bigger, 10x more per compute per year. but deep learning is getting more efficient. So GPUs are getting better faster than Moore's law, but algorithmic progress is even faster than GPU performance. And as I say, megaflops. Okay, so
I'm sorry,
Yeah, please.
when you say algorithmic process is progress faster than GPU improvement. In your slide earlier, maybe I misread it, I thought that. Could you go back to the blue and yellow?
okay, yes, okay, good,
So
so yes, you're saying
17 million is larger than 22,000.
sure, indeed, but this is not asking, this is not the contribution from GPU improvement. This is how, like, if we think about going from a cutting edge model in 2014 to the cutting edge model in 2020, like right before 2023, right? The question is like, how did we get better performance from one to the other, right? And a bunch of it, we just used a whole bunch more GPUs. And then the rest of it, we got algorithmic progress, right? So, but for the comparison of like algorithmic progress versus GPU progress, we can think about that previous chart. So, you know, I told you here, we have a doubling, in this case, it's every 6 months. We generally would find it like every 8 months. So well more than a doubling every year. Whereas for hardware, right, we saw that the gap between the compound growth rate for performance and price was about 45% per year, right? So it's, I've been comparing the 45% to the more than doubling. Yeah. Okay. And we've already talked about this. Okay. So I now want to pour a little bit of cold water on this good news story, right? Because I think it's fantastic that we've gotten so much improvement in algorithms in general, right? And so much improvement in deep learning, algorithmic improvement. But we also need to think about the limits of this. And in particular, I want to go back to Ada Lovelace's quote, and come back to this point where she says, reduce to a minimum, right? Because for these problems, there is often this theoretical limit of how well you can do, right? And people theorize that this is also true in deep learning. We don't really know what these are yet, right? But that we're going to sort of get to this minimum. And so what does this look like? So let me give you another example from some of our earlier matrix stuff. So matrix chain multiplication comes in when this situation where you have one matrix and another matrix and another matrix and another one. And you have to figure out what's the order that you want to do in order to minimize the number of operations, right? If you do it in the wrong order, you get really, really big matrices that you're multiplying. You don't have to do that. You can often pick it in such a way that you minimize them. So when this problem was first proposed back in the 40s, or actually earlier, but it comes in the 40s, the brute force version of this is exponential, right? You have to try all of the different combinations. That's not a very good way of doing it. And you can prove that you have to do at least a linear search in order to do this problem well. Then we move forward in time and we see that in 53, Godbout comes up with a better algorithm for this. So now we're down in cubic and cube time, right? And then in 81, Hu and Xing come up with a better one yet. And then in 1991, Ramanan proves that you actually cannot do better than n log n, right? And so we actually have now converged to this one, and later Bradford and Chabella showed it in a different way as well. But the really important thing here is, from at least an exact algorithm point of view, after 1991, you cannot get more, right? This is the theoretical best you could do for solving this problem. And so we thought, okay, this is very interesting. Let's go back to all of those algorithm problems we had before at the beginning. So not AI, but specifically the more general ones from the textbooks, and say, how often is this an issue? Well, 2/3 of the time. Okay, so there's 15% more of the time where there's a sublinear gain, not very substantial, 7% linear gain, 12% polynomial, only 1% exponential. So for these well-studied problems, we've actually done a lot of what we can in order to make these things more efficient already. All right, so when I saw this, I felt very mixed about this, so let me illustrate that, right? So great news, most important algorithm problems already have optimal algorithms, right? This is a real triumph for mathematicians and theoretical computer scientists, right? We are smart enough, we have proved that we have the optimal one.
The definition of important here is you know, it's if you define important as things we looked at for a lot, then it means that you know what I mean.
Okay, fantastic question. All right, so before I get to my other punchline here, right, we define this by importance by like what we teach our students.
So most will study problems have optimal algorithms. What's gonna be important tomorrow, none of us knows.
Okay, well, right, I mean, you would hope that the mathematical foundations of a lot of these things are pretty reusable, right? But absolutely, right, that we know that we're gonna expand out, right? And that will lead to different things. Interestingly, we have looked at that a little bit, and what you see is that because we now have better tools and better theorems and stuff, new ones tend to jump much more quickly to optimal, right? So someone introduces the problem and people pretty quickly are like, I can use this, and you know, sometimes we can, but yeah, absolutely. But I also want to say more generally, right, we've defined important here as in this particular way, we've looked at it in a bunch of other ways as well. So we've looked at, for example, like what gets put on Wikipedia as a measure of like what people care about. We're right now building a big database of which algorithms firms are using as a way to characterize this as well. So this implicitly, there's some weights here, which, you know, I haven't done anything fancy with here, but it is worth saying that's a very important question to ask, like, if you reweight it, what does it look like according to things that matter most?
There are also algorithms that are sort of between. It's an abstract algorithm, you've got to be optimal, but it matters how you use your cache and your memory, your disk, and your context that you have support.
Absolutely, and for those who I don't know Charles Lyserson, so maybe you used his textbook. He's one of my colleagues at MIT, and we're currently working on a project about performance engineering, which is exactly that last piece of, you know, okay, you know the algorithms, you know the hardware, but how do you mix them together? Okay, that's great. Okay, so coming back to this, so the good news is triumph for all of these, you know, wonderful theoretical computer scientists who figured this out. The bad news is most important algorithms, problems already have optimal algorithms, right? Like if we want more progress, like this is a problem. And okay, so, and as we've just hinted at here, you know, we need to be careful here. Like we can't have approximate algorithms, we can't have sublinear algorithms, right? Maybe you only just care about sampling, that's enough. Maybe you go to new domains, maybe there you find, oh, now we can make some restriction on the problem, and now it's much more solvable for them. So you can get more improvement. Okay, so let me just summarize overall. So what I told you is that algorithmic progress has been extremely rapid, often rivaling Moore's law, but progress is sporadic, happening in big steps, right? So it's much more likely to transform what you can do and then be stable for a long time, whereas Moore's law was much more of a continuous thing that you can count on. Deep learning success relies on using large models to flexibly model data. This is made possible by faster GPUs and even more by algorithmic progress. Just we don't usually see this. And the key question, one of the key questions my lab is working on now is this idea of how much longer can we fuel algorithmic progress, right? So if you think, for example, of deep learning, right? It's great to say we've had this incredible improvement, right? And in fact, in the data we've looked at, we don't see a slowdown. It's still going strong. But we know there should be at some point some limit on how well this is representing the data. And at some point we know from, for example, like if you start to prune the network or stuff, you tend to lose performance. We should expect there are going to be these things where as you try and get it down, you get into the sort of approximate algorithm world where you can decrease the amount of compute, but in doing so, you're going to hurt the quality of your answer. So that is, I think, a really big important question for sort of what the footprint of AI looks like in the future. Don't know the answer yet, but hopefully at some point we'll have that for you. I'll stop there. Thank you.